So this is what we're down to. I'm going to go on to electrochemistry and come back to thermodynamics, but I think we're done with everything before that, at least in as much as I feel like we can get in. So I'm going to start with electrochemistry, and this is really based on so did y'all cover redox reactions last semester? A little bit. If you were in my class, we did a little bit. Anybody other than my class, did you cover it? Okay. So redox reactions, that's what I want to do. The basic idea is these are chemical reactions where, for instance, you have something that's happening here is, I guess I better do, that is gas, this is a solid, and that's a solid. If you just did this reaction, what's not showing up in this equation is the transfer of an electron. So if I have neutral sodium, I guess I'll say 2, and I just take the sodium here. What's the charge on sodium here in the NaCl? The charge on sodium? Huh? Just going back to basic stuff now. So what's the charge on sodium when it's an ion? Huh? It's +1. It's +1, right? But I'm going to say there's 2 of them. I'm going to say 2 electrons. This is neutral. If I've got 2 positive charges, I have to balance it with 2 negative charges. There's my 2 electrons. And I'm going to say, here's what happens to the chlorine. 2 gas. What's the charge on chlorine when it's an ion? One minus. So 2 Cl1. So there's 2 negative Cl's, and this is where the negative comes from. Okay, rather than focus so much on that, let me give you this. I brought up the PowerPoint and I pasted the thing from the chapter. So oxidation number, also sometimes called states, oxidation states. That one's obvious. Same as its charge. All right. Zero, it's elemental. And the last rule is hydrogen is +1. two rules for hydrogen, oxygen. Do the exceptions there. Okay, let me just leave that small set of rules there. And just to show you, so if I have an ionic compound, I already did NaCl, CaF2. So ionic compounds. What is the typical charge on calcium? Huh? 2 plus. And what's the charge on fluorine here? If this is 2 plus and there's 2 fluorines, so fluorine is 1 minus. These, in this section, we're going to call, that's its oxidation number, its oxidation state. So it's exactly the same as what you already learned for ionic compounds. So that's really this first rule. It's the same charge as when it's a monatomic ion. All right, the next rule is its oxidation number is 0 when it's elemental. So here's some elemental things. F2, Cl2, Br2, H2. What if you just had argon gas? What if you just had calcium as a solid? Anything else, any metals that are just solids? Aluminum as a solid. These are all elemental, meaning the oxidation number for fluorine in this compound is 0. Chlorine here at 0, bromine is 0 here. So that's what this is saying. When it's elemental, and that just means only one type of atom is in the compound. We frequently see metals like this with an S, saying solid. I'm forgetting some simple gases here. What am I forgetting? Whatever. But these are the gases. Those are all gases. So those will be 0. So hopefully that's easy. Okay. Polyatomic ions. Let me show you the process for this. If I have gallium OH. So it helps to be able to recognize some of the polyatomic ions. This is Ga, H2, it's 3. All right. There is a oxidation number for each atom here in this. But if I wanted to go ahead and split this into OH and Ga, what's the charge on Ga? If I tell you the charge on this polyatomic ion is -1, there's 3 of them, what's the charge on gallium? 3 plus. So the oxidation number for gallium here is 3 plus. All right, I need to get the oxidation number for H and an oxidation number for oxygen. Oxygen is just about always going to be -2, so it's a good place to start. But there's also this rule is, so I have hydrogen here, it's bonded to oxygen. So hydrogen is bonded to a metal or a non-metal? Non-metal. When hydrogen is bonded to a non-metal, it's +1. So in this case, hydrogen is +1. All right. And then there's this rule about the sum of the oxidation numbers has to be the charge on the polyatomic ion. So if H is +1 and oxygen is -2, that's how we have this overall charge of -1. Meaning I have oxygen, I have hydrogen, together they make negative. Hydrogen is +1, oxygen is -2. The charge is -1. This hydrogen is +1. The oxygen is -2. Yeah, and they sum up to -1, which is what the charge is on. So that's OH. So this one, so oxygen is -2, almost always going to be -2. Hydrogen here is +1. The ion here is +2. There's my 3 oxidation numbers. So we hone in on the oxidation numbers to decide where the electrons are going for redox reactions. So that's what we're on our way to doing here. I uploaded 2 PowerPoints today. The other PowerPoint just has a bunch of examples in it. SNO2. Is that an ionic compound? How do you tell if something's an ionic compound? The easy way to say it is, it's a compound that has metals and nonmetals. That's a metal, that's a nonmetal. That's how you know they're charged. What's the typical charge on oxygen? -2. So if this charge is -2 and I've got 2 on them, I have a total of -4 for the negative. There's no charge up here. There's not a +3 or a negative or anything, so I'm going to say equals 0. So what do I need to put here to make this equal 0? +4. There's only one SN up here, so that +4 all goes on here. So here, the oxidation state or oxidation number for oxygen is -2. It's pretty much always going to be that, almost always. And the oxidation state for 10 is +4. But those are the same charges you would get if we were all the way back in 1211 and we were talking about ionic compounds. And I said, what's the charge on 10 here? All right. All right. It helps to be able to recognize the polyatomic ions. I don't mind giving you that chart that's got all of them in it. But the way to start here to figure out what's the oxidation numbers for all these atoms. You know what the charge is. Well, if you recognize that this is a polyatomic ion, you can probably already go, this is an ionic compound. These are nonmetals, but they make up their own little molecule that's charged. And then we have Na3. So if I pop the Na3 off, or the 3 NAs off, what's the charge on the sodium?
+3. Or +1 each.
+1 each. That leaves me with PO4. And what's the charge on PO4? If it's neutral up here, this is neutral, everything cancels up here, so. -3. So we've already identified the oxidation state for sodium as +1. To finish this out, I have PO4, 3 minus. All right, so I'm going to do this. I'm going to assume oxygen is -2. -2, -2, -2, -2. There's 4 of them. So -2, -2, -2, -2. Those come up to a total of -8. I do have a charge up here, so I'm going to put -3 here. What do I need to put here to make this true? +5. There's only one phosphorus up there, so it's plus. So there's my oxidation states. -2 for oxygen, +5 for phosphorus, and +1 for sodium. So generally the way to do these that are polyatomic ions, pop off this positive ion first and then analyze this by itself. NH2 negative. H2 negative. Yeah, okay. So hydrogen is bonded to a nonmetal. So what's the charge on hydrogen? Bonded to a nonmetal. So nitrogen is +1. Its oxidation number is +1. We have +1 then +1, we have a total of +2. What am I doing wrong? I've got a -1 up here. So what do I need to put here to make this true? -3 here. Nitrogen, 3 negative. If you were just looking at a periodic table and trying to figure out what's the charge on nitrogen, you'd come up with -3. So that's another way to come up with this. So in this case, hydrogen is +1, and nitrogen is 3 minus in this compound. Like I said, this is how we figure out where the electrons go in redox reactions. HClO4. I would tell you to start by popping the hydrogen off, which gives you H+, and then you have ClO4 minus here. You with me so far? When hydrogen's on the front, it's going to pop off as a positive charge because this is an acid now. So if you pop that H+ off, you with me there as a method? Oxygen, assume it's -2, -2, -2, -2, -2. You have a total of -8 from the oxygens. I have a -1 here. What do I need to put here to make this true? +7, so Cl is +7. Oxygen is -2, and hydrogen is +1. You with me? Why don't I just go CR, where'd it go? CR207. So let's say I've got that one, and I want to know what's the oxidation number for chromium and oxygen. Oxygen, there's 7 of them. Total of -14. There's a -2 up here, so I'm going to go -2. What do I need to put here to make that true? +12. Chromium, there's 2 of them. So how am I going to split that +12 among those 2 chromiums? 6 and 6. So +6 for chromium, -2 for oxygen. For that ion. The rule that's always here for oxygen is to accept superoxides and some other weird stuff, but recognizing the superoxide is its own skill that books never bother to tell you. Okay. So the charge on OH is negative as a polyatomic ion. What's the charge on aluminum? So we've got, and I already went through these. Oxygen is 2 negative and hydrogen is 1 plus. I think by convention, when we start talking about oxidation numbers, we start going +3 and -2 and +1 instead of putting the sign on the other side. I just kind of mix and match as I go, but you know what I mean. If I put +3 or 3 plus, I mean the same thing. Is this an ionic compound? probably need a periodic table sitting in front of it. But this is in the nonmetals, and this is a metal, so this is an ionic compound. Do you know the charge on sulfur when it's an ion? -2, just like oxygen. So I have no charge up here, so I'm going to say equals 0. What do I need here? You need +6 to make this equal 0. You've got 2 indiums, so it's 3 plus and 3 plus. So indium oxidation state is 3 plus, sulfur is 2 minus. Oxidation states. We did make a few of these. Oxidation states and redox reactions. So moving on to the reactions. Chloride. Okay, so here's a redox reaction. We can figure out where the electrons are going by figuring out the oxidation states. What's the oxidation state on this magnesium first? You guessed 2, and that would be true if it's in an ionic compound. It's that rule. That's elemental. So I'm going to put a 0 here. And when you have metals, not in an ionic compound, they are neutral. Well, let me just say this real quick. Three of the 4 compounds that atoms make. The other one is but we rarely talk about that. But covalent is, here's a covalent compound. This is a review. Do you remember Lewis structures? So what I've got here is the Lewis structure for carbon and the Lewis structure for 4 hydrogens. Here's what covalent compounds do. Because electrons tend to pair, those can pair, those can pair, those can pair, those can pair. That's what we call a molecule. That's a covalent compound. Those atoms came together because the electrons paired. Ionic compounds don't come together. Oh, and this happens between all metals. The carbon and the hydrogen, you get that pairing behavior between its only nonmetals. So if you're looking at a compound that it's all nonmetals, you know you're looking at a covalent compound. All those atoms came together because of the pairing of electrons. Ionic is some metals and some non-metals. So metals become ions, they become positive ions. Non-metals become ions, they become negative ions. Once the electron is transferred, it's the positive negative charge of the ions that make them stick together, not the pairs of electrons. So this is a review going back to 1211. And I just want to point out, so this is when things are ions. They aren't ions here, although you can get a covalent compound that's overall charged, like NO3 negative. So those are nonmetals. They make covalent bonds between the electrons, but they end up with an extra electron in it, so that's how that ends up charged. Metallic is when it's, so these are all only nonmetals. These are all only metals, and this is a mixture of metals and nonmetals. Ionic compounds are the mixtures of metals and nonmetals. Covalent compounds are all nonmetals. Metallic compounds are all metals. These are what you thought of as metals before you took a chemistry class. Things that go clang, things that are hard, they ring when you tamp them. Most metallic compounds have that property. So this is a metallic magnesium compound. There's no ions, the metals are neutral. Here the metals are neutral. Here the metals have their charge, their positive charge for ionic compounds. Okay, so I don't know why I felt like doing that, but that's a trip back to 1211. All right. So this one's oxidation state is 0. Is this an ionic compound or a covalent compound? You probably do need a periodic table in front of you. So chlorine is a nonmetal, nickel is a metal. So that's an ionic compound. So you can go ahead and go, I know the charge on chlorine, it's -1, right? Since there's two -1 charges, what's the charge on nickel? +2. Or I could have gone, the charge on chlorine is -1, there's two of them, so -1, -1, I've got a total of -2. There's no overall charge up here, so 0. What do I need to put here to make this true? And you would say +2. And then I look up here and go, there's only one nickel, so that +2 charge is on the nickel. Could have done it that way as well. But you see where I got the +2 for the nickel? I inferred that from the chlorine. Could be able to find it. The first row on the left on the periodic table, all of those are metals and they all become +1. The next row over, all of those are metals and they become +2. The only other one is aluminum that becomes +3. You jump across the gap, you get to aluminum, it becomes +3. All other metals have variable charges. So these are all +1, not counting iron, it goes to the non. These are all +1, these are all +2. Aluminum is always +3, and that's it. Every other metal on the periodic table, you can't predict the charge. You have to look at the charge. You have to infer the charge from the situation it's in. So nickel can be +2. I think it can also be +3. I don't memorize all of those. Okay. Is this an ionic compound or covalent compound? Metallic compound? This one?
Covalent.
Chlorine is a nonmetal. Magnesium's on the left side. So it's ionic compound. What's the charge on chlorine here? I could. So nickel is in the transition metals or the post-transition metals. So you can't predict its charge, but magnesium is in the second row. So you know the charge on magnesium. +2. So, and chlorine here is -1. So that balances. All right, what's the charge on nickel here? 0. Because it's elemental. All right, now watch this. Magnesium goes from 0 to +2. Chlorine stays the same, so I'm not going to mess with that one. Nickel goes from +2 to 0. And the only way that can happen is some electrons moved around. If magnesium went from 0 to +2, what happened to the electrons for magnesium? They left. And nickel went from +2 charge down to 0. That means it gained some electrons. All right. Here's our two important. That's where we get the word redox. There's oxidation and reduction, and they always happen together. When it's a reaction, electrons have to leave somewhere and they have to land somewhere else. So those two things always have to happen together. So I've just drawn an arrow for the two things where they changed. Do you remember which one is reduction and which one is oxidation? Losing or gaining electrons? Okay, I'm going to tell you how I remember it. Reduction is easy to grasp. If you look here and you go, magnesium went from 0 up to +2. That's what magnesium did. Its charge went from 0 up to +2. Nickel started at +2 and went down to 0. Nickel had its charge reduced. So nickel is being reduced. Think about it as the charge. Oxidation is it's kind of a historical anachronism. Everyone used to think it was, 200 years ago, everyone thought only oxygen could do this, and then they figured out that more than just oxygen could do this, but they kept the name. So oxidation doesn't say anything about something being increased or reduced. Oxidation is an increase in charge. Oxidation is happening to magnesium. Just to make it even a little more twisted for logic. Nickel is being reduced, but does that mean the charge is being reduced? Does that mean it's gaining or losing electrons?
It's gaining electrons.
It's losing electrons, because electrons are negative. That's why I said this logic has another twist here. If it's reduced, it gained electrons, because electrons are negative. That's how it took a positive charge and dragged it down to 0, because negative charges were added to it. So this one gained electrons and this one electrons. So definitionally, nickel was reduced here and magnesium was oxidized. You with me? Okay. Now, having already taken you through the torturous logic, in this case, magnesium was oxidized. Let me say it in a sentence. Its charge was increased. It lost electrons. It lost its negative charge. I'll also say so 4 ways to say the exact same thing. It was oxidized, its charge was increased, it lost electrons, it underwent oxidation. Okay. Still talking about magnesium. In this reaction, the compound that had magnesium in it is the reducing agent. It's a reducing agent because it can cause reduction in something else by giving it electrons. I know that's confusing, but you see what I'm saying? It's really kind of the English language that makes it like this. It was oxidized, it underwent oxidation, but since oxidation and reduction are opposite sides of the coin, we can say it was the reducing agent. We can also say it is the reductant. The ANT indicates the action that it has on another thing. So that makes things more complicated, or makes things more confusing. It is straightforward in a sense. If you get it straight in your head once, maybe it sticks. And then there's the flip side for nickel. I should say down here, NGS, because it's really this whole compound I want to refer to down here. So let me do all of this for you. Okay. I'm going to say nickel. Gained electrons, underwent reduction. But I want to say NiCl2. This is the so really the compound that the nickel was in is the oxidizing agent that was put into this reaction. The oxidant. There's one more. You can also say reducer. You can also say oxidizer. Oxidizer. Okay, there's your review. Did you guys balance redox reactions? You didn't? I seem to be skipping that in my 1211 class. I think when it comes to electrochemistry, that's part of the curriculum. Sorry. What else would we do here? Before I try to balance. All right, let me familiarize you with this. Camera can't see this, but let me open. If I go to content, and then PowerPoints, where I upload all the PowerPoints. I put two today. I put one that's called redox reaction, and one that just says April 6th. April 6th is the notice I'm going on. But if you look at this one, it says redox reactions. I have it here. So this is sort of like extra problems you can go through. This whole first page, you could go through this. I just used some of these earlier to find all the oxidation states. And then starting next from here, the process goes like this, and this is what I just showed you. You split the oxygens out, -2, -2, that means -4. No charge up there. So that needs to be +4, so 10 is +4. So I do a couple like this. I forgot what TA is. Anybody know? I don't know what TA is called. But if you had TA203, TA is definitely a metal. So you do it just like I did before. KBr4. So you can look at this to remind yourself how to do these. What, 6 in that one? So here's just a handful of more examples you could go through to make sure you understand it. Next is redox reactions. I've got a bunch of these in here. there should be more of these, but let me just point out for each one of these, I can't remember if I guess I just did a few of them. But I have also on there, phosphorus here, had its charge increased, it lost electrons, it's undergone oxidation, it has been oxidized. So just all this stuff that I just wrote on the board. It is the reducing agent, it is the reducer, it is the reductant. So you just have to pay attention to vocabulary when you get questions on these, rather than going backwards. So that's, I think that's useful to look at, and we've done several semesters ago. Let's do a few more of these. Redox reactions. And see, solid. Nice. Okay. Zinc, is that a metal or a non-metal? It's a metal. And CO3 is, those are nonmetals. If you split this out, you probably need you probably would need the list of polyatomic ions for this one, because zinc actually is always 2+. It's the exception to the transition metals. So if I did this, then zinc is 2+, because that's the charge on zinc. If I have this left, and I need to know the charges on oxygen and carbon, what's the charge on oxygen? -2. Just think of that as always being true. There's 3 of them. 2, 2, 2. -6. Charge up here is -2. So what needs to go here? 4. So carbon is +4 and oxygen is 2-. So I've got those. I'll write up here +4, 2-. All right. Is this an ionic compound? It is carbon. There's something wrong. Oh, yes. This is not a redox reaction. So let's move on. There's a section that says, tell me whether this is a redox reaction or not. If we went through all of those, we would find none of them changed their oxidation state. Carbon didn't change, oxygen didn't change, zinc didn't change. But let's deal with it. PCl3. That's a ionic compound or a covalent compound. This one's just going to end up being the charge as you expect it to be. What is Cl usually?
-1.
What is phosphorus usually?
-3.
+3. So those balance. What's the charge here?
0.
0. All right, if Cl is -1 here, what's the charge on P?
+5.
This one's -1, okay.
I see it +5.
If Cl is -1, there's no charge up here, so 0. What goes here to make this equal 0? There's only one phosphorus up here, so that whole charge goes on the phosphorus. Okay. This one is a little confusing in the sense that you could look here and then look here at this chlorine and go, chlorine didn't change, but chlorine did change here. And then phosphorus went from +3 up to +5. So +3 up to +5, 0 down to -1. Which one of these was reduced?
Cl.
Cl was reduced. Its charge went from 0 down to -1. Phosphorus was oxidized. Which one gained electrons? And electrons.
Cl.
Cl gained electron, and phosphorus lost 2 electrons. Okay. Do you know what this reaction is called in general? I tend to kind of hop right over this when I teach 1211, but it's such a classic I shouldn't. This is a combustion reaction. Combustion means you have some kind of carbon compound. There's always oxygen here. There's always CO2 and water. It's basically flames, anything that burns, that's what's going on. But all combustion reactions are also redox reactions. So there is electron transfer going on here. What's the oxidation number for oxygen here? It's easy.
0.
Yes, it's 0. It's elemental. So you never got 0. When hydrogen is bound to a nonmetal, which carbon is, what do we consider the charge for that? It's negative. This will be -1. All right, and if I've got 4 of them, -1, -1, -1, -1. Total of -4. There's no charge up here for this, so it equals 0. I need to put a +4 here to make this true. There's 2 carbons up here, so I have carbon 2+ and carbon 2+. Carbon is 2+ here. You with me? Follow the logic? Okay. Now let's go over here. If oxygen is -2, there's 2 of them, total of -4. There's no charge up here, so equals 0. I need to put a +4 here to make this true. There's only one carbon up here, so that whole charge goes on carbon 4+. So you see the carbon changes. Oxygen was 0 here. Over here, for H2O, oxygen is going to be -2 like usual, and hydrogen is going to be +1. -2 +1 +1. That's true. Just remember that for H2O, this is one of those weird rules with oxygen. But in H2O, this oxygen is what you expect it to be, -2. That forces that to be hydrogen to be +1. -2 +1. What am I getting wrong here? -2. Got too much going on now. -2 -2, which makes that +4. That becomes -2. +1 combined with nonmetals. I do this every time I do a combustion reaction. I get stuck. I can't figure out why this can't be -1. It's supposed to. Then this would be charged +3. I'll come back to combustion reactions. I'm just going to stand here confused. This has to be +1. Maybe that's why I ignore combustion reactions. They confuse me. Let's do one more. It's not combustion. And then we'll go on to try to balance these. CO2. All right, let's do zinc solid plus what's the oxidation state here? H is on the front here. If I took 2 H's off, I'm left with SO4, 2-. That's on the polyatomic ions list. So I'm going to say +1 for hydrogen. Okay, +1 for hydrogen. And then I've got a -2 here. I've got 4 oxygens, so -2, -2, -2, -2. -8. I'm going to put a -2 here. So what does this need to be to make this true? This has to be +6. There's only one sulfur, so that whole +6 goes on the sulfur. Oxygen is -2. SO4 is going to be the same here. It's the same ion. So everything I do here is going to be the same. So -2 +6, 2+ for zinc. And hydrogen here is going to be -1. Hydrogen is a nonmetal, so hydrogen, oh no, it's not. It's going to be 0, right? Because that's elemental. You with me? We just went over all this at 12:11, still screwing up. Okay, zinc to zinc. The sulfur and the oxygen stays the same. Hydrogen to hydrogen. Okay, which one of these goes down in charge across the arrow?
H.
So that one is reduced. So zinc is oxidized. Gained electrons, underwent reduction. It is the oxidant. It is the oxidizer. You with me? That's a review of redox reactions, at least as I do them in 12:11. Okay, what I want to do next is balancing. You guys balance these? You balance it under base conditions, you balance it under acidic conditions. Good. This book did that in the 12:11 portion of class, and I started to do those, and then I stopped myself, but it does go here. Okay. So, balancing redox reactions. So you're given this as a starting point. Seven. This is 3 plus. So, and this is without their counter ions. I could put K2 Cr2O7, that would balance. I could put OH or something here. But this is sort of like a skeletal description of the reaction, the backbone of the reaction. Ignoring oxygen. What's happening to iron here? Goes from 2 plus, it's being oxidized, meaning it's gaining or losing electrons. Loses electrons. And ignore oxygen here, chromium. So 7 oxygen, minus 2, minus 2, minus 2, down to negative 14. Minus 2, we already did this one. What do I need here? I need a plus 12. I split the 12 here, so this was 6 plus there. And it's become 3 plus here, so it's gained 3 electrons. Right. So what you got to do from here is to balance it. You start by splitting it into those 2 reactions. Split it into that. It's Cr2O7 to minus. So I'm going to work with these. We first want to balance everything except any oxygens or hydrogens that are there. So if I set a set of rules, the set of rules is in there, but I'll say first split it into the half reactions, which are what these are called. 2. So any oxygens and hydrogens there, ignore those for now. So to balance that, there's one iron here and one iron here. That's good. I've got 2 chromiums here, so I've got to put a 2 here. And I'm ignoring the oxygen. So ignore the oxygen and hydrogen first. You with me? 3 is, now we balance the oxygen. So if I want to balance this oxygen over here, I need 7 oxygen. So I'm going to say 7 H2O. All right, the only thing left to balance here is the H2O, the H's. So I'm just going to put over here H plus. If I'm doing it right. Okay. This is a 2 plus, and this is a 3 plus. So where does the electron go? It's off by 1 charge, so I'm going to add 1 electron. Do I want it over here, or do I want it over there? One electron. The point is, there's a plus 2 over here, and plus 3 minus 1 is plus 2, that balances it. It's sort of like saying I'm a plus 2 here, but if it will just lose an electron, it'll be a plus 3, and there's the electron lost. The electrons over here are going to be on this side. Plus 2 minus 12. I'm looking at the wrong spot. So chromium here is plus 3. And I've got 2 of them. So how many electrons? This was plus 6. Actually, I had Cr plus 6 and Cr plus 6. And here I have Cr3 plus, Cr3 plus. So the electron in this case is going to go on this side, but how many of them do I need? Maybe 6. Yeah. Add 3 negative charges to this plus 6, and then I'll get plus 3. Add 3 negative charges, then I get a plus 3. So 6 electrons on that side. One more step, did I not save it? One more thing to do is to make this number of electrons and this number of electrons the same. So what I need to do is multiply. I think I just multiplied by 6. I don't know why that seemed wrong. What I'm saying is I multiply all of this by 6. think that's right. 6. Yeah, that's right. And then 6. Okay. Yeah, I'm doing this right. So from here, anything that's the same on both sides, you can eliminate, which is going to be the electrons. There's that. So I end up with 6 Fe 14H plus. Yeah, I did this right. Cr287, okay. So once I multiply through by that, I can eliminate the electrons because we're in balance now. And then, so this reaction balanced is and that's the answer. Okay, that we balanced. We balanced that one under acidic conditions. To do it under basic conditions, just to be sure. Okay, for now, what y'all should do. These that I added, oxidation states, make sure you can do these. This is just finding the oxidation states. So you can practice those and you can also look at this. Do look at this because it kind of has everything except balancing. This. So look at this PowerPoint, make sure it all makes sense. And look at these quizzes. But look at the quizzes on there. It goes over finding oxidation states, identifying what's being reduced and what's being oxidized. If I think we need to, I'll go over balancing under basic conditions, and then we can actually talk about electrochemistry. That is how batteries work. But yeah, let's just stop there. Yes, we're okay. We'll make it. I'll get your test graded by Wednesday.